All right. Looks like we need a few more people showing up here as we get started. All right. Going to get started here. So let's take a look at things. So we left off before I kind of talked about the results for the survey. So you can start crunching those numbers. You can start doing the parts of the project that are due in those discussions inside of Canvas. Those are the easiest parts. Those are the easiest points to earn that go towards your project. So the whole project is worth about 200 points. You know, and those points are counted differently than the homework points because half, you know, they're weighted. But of those points, about a third of them come from the discussion assignments. And I tend to grade those discussion assignments pretty easy because you've just learned them. So as long as you've done what I asked you to do, and it's, you know, it shows that you've gone in, you're trying to learn how to use StatCrunch the proper way, you're saving your, like you're doing something moving towards the project, I give you those points. That doesn't mean that those things were done really, really well and are A work. It just means you're progressing towards getting to the project being done. The final project is graded a little bit harder, so it's nice to have those early discussion points in there because it helps pad your project grade a little bit. But those dates are coming fast and furious, right? So make sure you're getting those done so that you can complete things, you know, the final project in a way that is both on time and of good quality. Okay? Okay, so with that said, we've got a couple things I want to talk about. So we started talking last time a little bit about measures of center, and why we actually have two major ways that we measure center. There's really like a total of, I don't know, 5 or more, but like the mode doesn't come up that much. It kind of just comes up in very specialized situations. The mode is the answer that was used the most often. You could go, yeah, I could see how that would be a measure of center, but usually not as helpful. The two big ones are the mean and the median. Okay, so the mean and the median are both measures of center, but they're different measures of center, right? And then sometimes, you know, people just want like a specific answer. So a lot of times people are like, well, which is the right one? Well, it depends on the problem that you're doing. It depends on the question that you're trying to answer, whether you should be using the mean or the median, right? So what I want to do is give an example to show you that it depends which one we're talking about. Oops. Sorry, I thought I had some food in my teeth there. So let's do an example. So we can pull up StatCrunch and we can make an example pretty easily. So let's put in some home prices here. So 500,000, 550,000. 550,000, maybe 600,000, 625, maybe 525, maybe another 550, and then, you know, maybe another 625, 650. Right, so we've got some home prices there kind of ranging around 500,000 to 650,000. So a little bit of a range. Let's just say the situation is that you're going to go looking at homes. You want to look at neighborhoods. You're in the neighborhood, or you're in the market for buying a house. And obviously you don't want to spend time looking at houses that are not in your price range. So you're going to look at homes that are in your price range, right? Well, how do you kind of know? So you go, well, I have a specific price range that I'm interested in, and I want to know, I want to go to those, right? There's lots of different neighborhoods around. I don't want to spend my time in something where the homes are too, you know, maybe too priced too low because I want to, I want to be in a little bit better neighborhood or something, but I can't afford the really expensive neighborhoods. I just want to focus on the ones that are the right price. Okay. So, you'd let if someone's showing you around, or if you're using Zillow, you'd put this information in there and it would help you figure it out. Well, let's take the mean and let's look at the mean and the median for this one right here. For this example, if this is a neighborhood, there are homes in this neighborhood selling for these prices. So let's take a look. So if I go to stats, summary stats, columns, variable 3, compute, what do I get? I get a mean of about 578,125. I have a median of about 575,000. Those values are pretty close to each other. The mean and the median don't have a lot of distance between them. So in this case, there isn't a big difference between using the mean or using the median. They both tend to agree quite a bit. Okay, so you go, okay, fine. So, you could tell you could look up, well, what's the mean home price in this neighborhood? Okay, yeah, that's I see what's going on there. All right. But usually we don't use the mean. In real estate, they don't use the mean home price. That is very rarely done, and you're about to see why. So let's say there is one home in the neighborhood that is extra big. It's up on the hill. It's got a great view. It's absolutely massive, like a mansion, right? There's a couple of homes in my neighborhood that are just enormous, right? Like they just make the rest of the homes look like, we live in little rocks or something. These homes, there's like four homes that are they're like mansions. They're huge, and they're up on the, hill. They've got a view, right? So they're worth quite a bit more than the rest of the homes in the neighborhood. So let's just say that there's a home that is $1,750,000 for sale. Okay, so we have the same homes we had before, but now we have this other home which is $1,750,000 because it's massive. It's 3 stories. It's over. You got a huge lot overlooking the city, the nice view. It's got all that. So now let's run those summary stats again. In fact, let me go ahead just so you get in the practice of this. I'm going to rename this house price. See, so you can rename the column. That's really helpful to make sure I grab the right column. When I come in here, hit summary stats columns, let me choose house price, compute. Oh, we have a little difference here. A little bit of a difference. Look at the mean now is $708,333. The standard and the median is $600,000. That is starting to be a difference. That's a difference of $108,000. That's quite a bit. Before, the difference was about $3,000 between the mean and the median. Now it's $108,000. So those values are not so close anymore. One of them, in this case, is a better measure than the other ones. Than the other one is, right? So which one do we think is a better measure here? Well, if you were looking for the neighborhood that was going to have the right prices for the houses that you wanted, if someone said, well, the median home price in this neighborhood is $600,000, well, I would say that's representative because there are some houses below $600,000, some houses above $600,000. $600,000 is kind of right in the middle of the values for 8 of the 9 homes. I would say the median is a decent representation. It's not great, but a decent representation for the middle of most of these values. But look at the mean. Right? If you looked online and you said, oh, the mean home price in this neighborhood is $708,000, and then you went to that neighborhood, you'd be disappointed because there's no homes for sale near $708,000. There's a whole bunch that are like $60,000 and further away, right? So I'm confusing things with the way I'm saying that. But you see, the highest price of these, the bulk of our homes is $650,000. We're $60,000 above that. And then some of the homes are like $200,000 below this mean. So we went to this neighborhood thinking, oh yeah, if I'm looking to spend around $708,000, that's what the mean is. And I get there, and yet most of the houses are either way below the price I'm looking to spend or way above the price I'm looking to spend. So in this case, the mean was not really a good representation of the center because it wasn't helpful. I just wasted, however long it took me to get over this neighborhood. It wasted my time because none of the homes are the price that I'm looking for. But the median was still pretty good. If you're in the neighborhood for a house, or you're in the market for a house that's about $600,000, you get here, you're going to go, oh yeah, here's some houses around $600,000. There's some stuff in that range. So it's important to understand that both the mean and the median are very useful measures of center, but sometimes one is a better measure than the other, and it really depends on a few things. Notice in this case, do you remember what we called this point right here? That's an outlier. This home that's like, 3 times what some of the other homes in the neighborhood cost, that's an outlier. That data point is way off by itself. And we talked about this, I don't think last time, but 2 meetings ago. The mean is affected by outliers. So once you throw an outlier into your data set, the mean can really get skewed, right? It can really change that mean value. But the median, not as much, not as affected by outliers. So the median is not as skewed by that data. So in this case, I would say for the example I'm giving, the median is a better measure, and you almost hear that. You won't really hear a real estate agent talk about the mean home price in a neighborhood. You regularly hear them talk about the median home price in a neighborhood, and this is a perfect example of why that is. Now, every situation is different. This is why in statistics, it's hard to have a hard and fast rule. It's hard to just say, always use the mean, or always use the median, or in this situation, always use the mean, or in this situation, always use the median. It's hard. Every time that you do a statistics problem, it's different, right? It's not like in math when we're solving equations, like once you've solved 20 quadratic equations, you solve that next quadratic equation, it's pretty much the same thing. Sure, there's different numbers in there, but you're like, it's the same. I'm just going to use the quadratic formula or whatever. It's, you go through, what you're doing. With statistics, it's always a different game because it's not, in statistics, you rarely ever just do statistics on a set of numbers. No one says, you know what, I have my favorite set of numbers and I'm just going to do statistics on that set tonight. That's how I'm spending my evening. I'm going to have a glass of wine and my favorite set of numbers and I'm just going to do statistics. You do statistics because you have something you're trying to discover. You're trying to understand something better. You're trying to figure out, how to run your business better, or you're trying to improve medical science, or whatever it is you're trying to do with statistics. Every problem is a little bit different. If you're doing a problem for, you're trying to figure out how to better sell cars, that's a little different than doing statistics on a set because you're trying to show that a new medicine works better than the previously available medicine or whatever. You always have to make these different choices. So I know that's frustrating for students because students want to go, well, just tell me the answer. Just tell me when to use the thing. All right, there's the mean and the median. Just tell me when to use the mean and just tell me when to use the median. It's not that simple. Statistics takes a lot more critical thinking. You have to pause and you have to go, okay, what's really going on here? So you kind of have to respect that narrative. You'll hear me bring this up numerous times throughout the semester. When you're doing statistics, what you're really trying to do is construct a narrative. You're trying to construct a story about your data. You're trying to say the data shows us this, and this is the evidence that I have for making that claim, right? So the evidence is trying to show us that this new medication we developed works better than the ones that are currently on the market, and here's my evidence for that, right? Or we can speed up the production factory line by changing to this new system, and here's my evidence for making that claim. So, you want to think of it like you're in a courtroom, you're a prosecutor, you're trying to construct a narrative about that defendant that you think did something bad. You're constructing a story for the jury or the judge, and then you're going to give evidence that backs up your story. That's what we're doing with statistics. You're constructing a story about your data, and you need to back it up. So that's really how you decide, well, when am I supposed to use the mean and which one am I supposed to use the median? When am I supposed to use the median? You use the one that best backs up the narrative that you're trying to give. Now, by that, of course, I mean doing it ethically, right? There's other ways you can do it where, like the oil companies have done this, the cigarette companies did this for years, where they were very selective in their statistics so that they could back up the claim that they wanted to make, which is this cigarettes aren't addictive, this kind of stuff. I'm talking about doing it in an ethical way. You're not trying to mislead people. You're trying to give them the evidence so that they will be convinced of your point of view. So if the mean is the thing that best authentically represents the information that you are trying to convey, then go with that. Right? Now, what I will say is usually the more outliers you have, or the more severe outlier that you have in your data, the mean becomes less useful. So if you have an outlier or you have numerous outliers, then you probably should start thinking about using the median, right? Just like the example we used here. The median was a better choice because of this one big outlier. You'll notice that when you, in the absence of outliers, your mean and median start to match up. They start to be close together, and then it doesn't matter as much, okay? But I would say by and large, I usually would tend to use both the mean and the median. It's okay to use both. You can measure both and say, well, we found this to be the mean, we found this to be the median, or you just go with the median, right? You can just go with the mean sometimes, but again, that's probably in the case where you don't have a whole lot of outliers. You don't have a whole lot of things throwing things off. So just keep that in mind. There is almost every single rule in statistics gets broken at some point, but you have to have a good reason for breaking that rule. You have to have a justification for saying, yes, the reason that I used the median in this case was because. It's not like you're just going to throw a dart at a dartboard and then have that determine whether you use the mean or the median or something like that. You want to have a good reason for why you're making that choice, because that's kind of what happens in statistics. You do a bunch of work and then people go, oh, okay, but what about this? And you don't want to go, oh, yeah, I guess I don't know what I'm talking about. You want to be able to say, oh, that's a good question. I chose the median because of this, or I chose the mean because of this. Okay, so I know it's frustrating from a student perspective that statistics doesn't always have those kind of cut and dry answers the way math does, but it's more like a philosophy course or something, sociology, where there's a little bit of like, there's more than one way to get to a certain place, and you just have to have a good justification for how you got there, right? Okay. All right. We'll probably come back to this. Let's move ahead. And if there's any questions, feel free to jump in there. Looks like we're getting a few more people coming in. So feel free to bring up questions along the way if you have any. So remember, the median is the actual middle value. So you have to rank your values, pick the one in the middle. If there's an even number, then you have 2 in the middle, and you take the mean of the 2 middle values. But by and large, you're going to have StatCrunch taking the mean and median for you, so you won't actually have to calculate that. Also, be careful. We don't use the word average. People always want to ask about the average of stuff, but to a statistician, they go, what does that mean? What do you mean by the average? We have a definition for the mean. We have the definition for the median. Which one do you want to know about? Because average is kind of this nondescript term that can mean numerous things. So you want to make sure that you're always using the word mean or median in this class. Don't say average, because that's kind of like measures of center. Well, it could mean a few different things. So make sure you say the one that you want. That's kind of a thing that happens in statistics. Okay, the mode is just the data set that came up the most, or the data point that came up the most. So if we looked at ages of students I don't remember what the data looked like, but the mode could be 18 or 19, maybe 20, probably 18 though. Probably the most number of students would be 18, right? So that would be the mode. Bimodal means you have two values, so maybe 18 and 19. Maybe those both have a lot of people coming in at 18 and 19, so it would be bimodal data. But We won't deal with the mode too much. You might have some in the homework, so you just want to be aware what it is, but we don't usually use it very often as the measure of center. Okay, let me get my place here. Where are we? Right, you've got means from frequency distribution. I feel like this is covered pretty well in the videos in the homework, so just follow along with that and you should be fine. Should be fine. Where are we? All right, skewed and symmetric. So symmetric, you've probably heard before. Symmetric, there's many types of symmetry. The kind that you probably have seen is like there's symmetry you can have if a shape is the same on both sides and you fold the paper over and the shape lines up on itself. We call that symmetry. But you can have rotational symmetry. You can have all sorts of different type of symmetry. We just mean if you have a graph and you fold it over on itself, does the left half line up on top of the right half? If so, then we would call that symmetrics. For instance, this graph right here, if this was a piece of paper and I folded it right on this pink line, the left side would line up on the right side. Okay, and you can see they're saying this happens when the mode equals the mean equals the median, right? Because we already kind of saw when the mean equals the median, you have probably not a lot of outliers. You have some pretty well-behaved data, so it's not skewed. Skewed is kind of like, imagine standing on one side of this curve and you push against this, whatever it is, this curve, you push against it, it's kind of going to pile up on the other side, right? It's going to look like this. If you took this and someone pushed right here, you get this kind of a shape. That's called skewed. That means our data is heavier on one side than the other. Imagine if I took this paper and I folded it on this pink line, well, this curve on the left is not going to line up on this curve on the right. Okay, it is no longer symmetric. It is skewed. And we can be skewed the other direction as well. One example of skewed data would be ages in this class, right? We get skewed data because the majority of people coming into community college are coming in out of high school. Okay, not everyone. There's still a significant number of people who come in at different ages, but a lot of students coming into community college have just finished high school and they are starting here. So they are 18. Sometimes people are coming at 19, but usually if you start at 18 and you stick around, you're still at the community college at 19. So we see a lot of 18 and 19-year-olds, some 20, 21-year-olds. You know, that's fine. I spent 4 years at community college because I couldn't pick a major. So I just kept taking classes till I figured out what a major was. But you're gonna see this kind of graph, right? You're gonna see a whole bunch of ages around 18, 19, 20, and then it's gonna level off as we get people coming in older. So you know, in these classes, I've seen these different surveys. You see a few people in their 30s, maybe a person in their 40s. I have seen people in their 60s at different times. But the further you get to the right, the larger the ages, the more this line is sort of decreasing. What about on this side? Well, it's also skewed because the school, you have to be at least 14 to attend community college. But if you attend community college at 14, there's special rules you have to follow because, you know, you're not technically an adult and, you know, there's all sorts of considerations at that point. So if you start the school at 14 or 15 or 16 or 17, you're under kind of different situations, and there's not a ton of students like that. I have had numerous 14-year-olds take my classes before. Most of the students who are younger and take our classes are great students, but there's not a huge demand for that, right? There's not that many 14-year-olds saying, let me go take math at the college, right? But there are some, so that's why on the left we're seeing this big fast drop-off, because once you're below 18, we don't have a whole lot of students at the college of those age. We get a few students from El Camino, we get a few students from Foothill, and like a handful of students from the other high schools in the area. But for the most part, people are waiting till they're 18 and coming. So you're not going to see this kind of symmetric shape for ages of students at Ventura College. You're going to see this, where there's very few students, 14 to 17, a whole bunch from like 18 to 22, and then it levels off slowly as the ages increase. So being able to recognize the shape of the data is very important. It's going to help you construct your narrative, because the narrative that you construct around a symmetric graph is very different than the narrative that you would construct around some skewed data, right? And this is one way to kind of tell before you even see the graph. If your mean and median are close together, you're kind of expecting to see something like this. Not necessarily, right? There's all sorts of things that can happen, but by and large, you're probably thinking, I bet this is kind of what's going to happen. As soon as that mean and median start to separate, that's probably indicating that you have some outliers. It might indicate that you have an unevenness in your data, just like we have for the ages, where people generally start at 18. It's almost like for most people, the doors are kind of locked until you're 18, and then it's just a flood of students coming in, so you get this kind of skewed data. You want to be able to recognize that and read that from your data when you make your visuals and the stuff that you're going to do, but also be thinking about it even before you get the visuals. You can kind of start to think in your head, I bet I kind of know what that data is going to look like when I graph it, right? But you don't know. Okay, so there's that part. Let's see. So that was the measures of center part. And then the other really, really big thing is measures of variation. We're really talking about the shape of the data, which we kind of just did a little bit. Kind of introduced the idea that, well, it makes a difference if something is symmetric or if it's skewed, right? That makes a difference in how we tell our narrative, and it does, right? Two things that you should immediately think, like step number one when you have data. So when you're looking at your columns in StatCrunch and they're the solutions to your questions, or they're the answers to the questions in your survey. I mean, technically step one, you could almost call it like step zero. The first thing you have to do is make sure your data makes sense. We talked about that last time. Go through, edit the values so that the computer can actually read them. But assuming your data is in the proper form, the first two things you're going to look at: what is my measure of center? What is my measure of variation? What is my spread? What is my shape of my data? Those are the first two things, because until you answer those two questions, you can't really start to answer the other questions that you need to know about. So remember how I said, I was talking about how every statistics problem is a little different, right? You treat a medical statistical problem different than you treat a sales medical problem, different than you treat a research problem. And even within research, well, if we're researching this, then we do it one way. If we're researching this question, we do it different. So every statistics problem is a little bit different. But before you can decide, well, how should I attack this problem, you need to understand the measures of center and the measures of spread for your data. And the first three things, you should look at, the two measures of center that are the heavy hitters, the mean and the median, and then the one we're going to see that is our heavy hitter for measures of variation, the standard deviation. If you don't have those three things, you haven't really started your problem yet, right? For one thing, all the stuff you do later, generally the calculations require the mean and the standard deviation. But also, you can't even begin to have an idea of what you think your histogram should look like or any of that until you've answered those three basic questions, and then you can move forward from there. So here's another example that I use in StatCrunch. So let's just look at exam scores for class 1, and then we're going to have exam scores for class 2. Okay, so let's just say I have a class. I have two classes, two identical classes, and I give those two classes identical tests. So like two statistics classes, right? We don't have tests in this class, but let's just say we had a statistics test coming up, and I give you the test, and then this morning I have another statistics class. I gave them that same exact test. Okay, so let's just look at the data that could be possible scores. So let's say I have one class where every student got an 80. Okay? Super consistent. Every single one of them got an 80 on the test. Okay? And then I have another class where some students got a 60, and then some students got 100. All right? So two separate classes, two very different outcomes to these tests. All right? Well, let's see something. Let's look at the stats, summary stats, columns, C1, hit compute. What do I get? I get a mean of 80 and a median of 80. Okay, so our measures of center for both of these are 80. That makes sense. Every score in there was 80. Okay, so that's my C1. Actually, I want to see if I can do this. Yep, there we go. So I've got my summary stats for both C1 and C2 at the same time. If you want to do what I just did, use shift-click. So if you shift-click the two things that you want, you can include both of them. Okay. Also, if you go down here, you can choose which statistics are being calculated. So it kind of does the basic ones. One of the ones you're going to have to do on the homework is this unadjusted standard deviation. We haven't talked about that yet, but it's a different calculation for a population versus a sample. And you have homework problems that are going to want you to calculate this. So you'll want to know where this is in StatCrunch. Okay. I'm looking at it right now. Okay, so if we go back here, what do we get? Well, my second set of data also has a mean of 80 and a median of 80. Well, these two sets, I would say these are very different. This was a highly consistent class where everyone had pretty good knowledge of the material, but not great. This was a class where half the students had terrible knowledge of the information and the other half had perfect knowledge. Those are two very different classes, but if we just look at the measures of center, the mean and the median, well, we can't tell the difference between them. We got 80 for all of those values. So what this is telling us is that the measures of center are insufficient to give us a full understanding of our data. They're not really showing the difference between these two sets. What we need is a tool that will show us the difference between this data and this data. And enter the standard deviation. There's a couple other measures, the range. These are pretty straightforward. But by and large, the standard deviation is the go-to. Anytime you do a problem in statistics, you're going to mention the standard deviation. It should be in there. So the standard deviation of a set of sample values denoted by lowercase s is a measure of variation of values about the mean. This is kind of a weird way of stating that. I'll give you the details in just a second. Well, I'll give it to you right now. So basically what they do is they take the mean of the data, and then they measure how far each data point is from the mean, and then they use all those distances to do a calculation, and it gives you a measure. So if we look back at our data over here, notice for class 1, those exams, my standard deviation, which is right here, it's Dev, standard deviation, is 0. My standard deviation is 0. Why is that? Because every single data value was equal to the mean. So the distance between the data value and the mean was 0. So when we did a calculation with a bunch of zeros, we got 0. Notice over here for exam 2, we got a standard deviation of 21.081851. So what it did was it took this value and it did 60 minus 80, which is negative 20. 60 minus 80, negative 20. So it wasn't getting zeros anymore. It was getting a measurement here. And then it was taking 100 minus 80 and getting 20. So it took all those values and it did some calculations, which you don't have to worry about because StatCrunch is going to do the number crunching for you. But notice that the standard deviation is not 0 because our data points weren't all right on the mean. That's really unusual, to get this, where every data value is the mean. But that's because I'm making up an extreme example so that you can kind of understand what's going on here, right? So there really is, if we try to use the same language, there really is no deviation in this first course where everyone got an 80. Super consistent, right? To deviate means to be different or to change. There's no change or difference in these values. Over here there is. There's some 60s and 100s. Those have some differences between them. They have some deviations. So that's why we get a deviation, standard deviation of 21 over here and 0 over here. It's telling us how spread out our data is. Well, for exam C1, the data is not spread out at all. And there's no spread. There's literally no spread. They're all just right at 80. Over here, there is some spread to the data, right? Over there. So that's that standard deviation. It's telling us how spread out our data is. And that's helpful because it doesn't mean everything's really tight in there where all the values are close together, or are they really spread out, right? Yeah, let's leave it at that, and then we'll talk a little bit more. So don't worry about the formulas too much. You'll deal with those when you're doing the watching the videos and doing the homework. Oh. Here's what I wanted to say. There is a different formula for standard deviation of a sample versus standard deviation of a population. So what does that mean? Let's remember what those terms mean. It may have been a while. Remember, the population is the whole group we care about. It could be the population of the United States if we're studying something that had to do with politics on a federal level, right? Oh, we want to know about all American citizens. So it's the population would be the American citizens. Or if it's just people, if you want to just know about people, not necessarily citizens, like that's when we do a census, the Constitution says we're supposed to count people. It doesn't say you're supposed to count American citizens. It says you count people, right? And that actually was fought in the courts during the last administration because Trump didn't want to count people who weren't citizens. They were trying to, change the way things are counted. And the courts said, well, the Constitution says people. We got to count people, right? So that's what the Constitution says we're supposed to do. So in that case, that would be your population. So you see how you can decide what it is you're looking at. Are we looking at American citizens in the United States? Are we looking at just human beings that are in the United States? Are we looking at Ventura College students? Or are we looking at people who go to Ventura College, like on a daily basis? Like, I go to Ventura College, it's where I work, but I'm not a student there. So you want to be careful about the way you define your population to make sure you're including the group that you really mean to. And as we mentioned before, you almost never get to measure an entire population. The populations are too big. You're not going to get, we could send an email out to every person with a Ventura College email address. We're not going to get 100% return on those emails. If we were to ask everyone a question, we would not get a 100% response rate. Not going to happen, right? So that's why what we do is we take a sample and we measure that. So this kind of throws people a little bit. The way we measure the standard deviation for the entire population is different than the way we measure it for a sample. So that's what I was showing you over here in StatCrunch is, if I pull this up, let's see, options, edit. If we go in here, notice how it's already including the STD dev. By default, it's going to give you the standard deviation. That is the standard deviation for a sample. Okay, you're going to have problems where they say treat this as a population, and you're going to go, oh, that's that other standard deviation, and then you're going to go down and you're going to find the unadjusted standard deviation, and you're going to use that one for those problems. All right, this is definitely a thing I see pop up in my office hours where people come and they're like, I'm getting this for the standard deviation, and they keep saying I'm wrong. That's because you're giving the sample standard deviation, and the problem is requesting the population standard deviation. So just be aware of that if you're getting stuck on a problem like that, okay? Okay, where am I? Right, and they even kind of point that here in the caution. If you're using technology, make sure you're using the right one, okay? There's also a thing called the variance, which you'll look at a little bit in the homework. The variance is the standard deviation squared. Now, there's reasons why we generally use the standard deviation over the variance, but the variance can have its own use as well. One nice thing about the standard deviation is it has the same units as the data that you're studying. Okay, that's helpful if you're studying something and your measurements that you were taking from people was platelets or something in their blood, right? And you have this unit, so platelets per cubic centimeter. Your standard deviation is going to be in platelets per cubic centimeter versus your variance, which will be the square of that. So what is a platelet squared? Like, we can understand what a cubic centimeter, well, even a cubic centimeter squared, what would that mean? But a platelet squared, I'm not even sure what that means. So it's sometimes just a little easier to think about in terms of the standard deviation, but the other one will come up occasionally. One rule of thumb you think about, so we started talking about data points and how far they are away from the mean. Once you have a data point that's more than 2 standard deviations away from the mean, it's probably worth looking at. Okay, it's like the same with an outlier. When you have an outlier, look at that outlier. That outlier may give you information when you kind of uncover the narrative for that value. You may learn something that you didn't already know about your data. Unusual data points can do that as well. You're asking yourself, why are these points different? What's going on here? What's different where I'm getting these other different values? So just be aware of that. We will revisit this idea of the standard deviation being used as a ruler. Like, you could measure the length of your wall with a ruler, right? I give you a 1-foot ruler, and you just keep putting that ruler after itself. You put it here, okay, move down here, and you just measure all the way down the wall, and you go, okay, this wall is 12.5 feet long. Okay, well, imagine we're doing that, but with the standard deviation, where your ruler is the standard deviation, and you're measuring how far is the standard deviation from the mean. And so you start at the mean, and you put your standard deviation down, put it down again, until you get to the data point. So, like, just sort of picture yourself putting a ruler along a wall to measure how long it is. It's the same thing we're doing with the standard deviation. How many standard deviations away from the mean is this data point? Right, that's your new ruler. Okay, some properties of the standard deviation. The standard deviation measures the variation among data values, right? Remember, we got in the class where everyone got scores of 80, there was no deviation. Our standard deviation was 0. That makes sense. That makes sense that in a class where there's no deviation, your standard deviation should be 0. Right? Values close together have a small standard deviation, but values with much more variation have a larger standard deviation. So the larger your standard deviation, the more spread out your data is going to be. Right? The smaller your standard deviation, the more clustered together all your data points are going to be. And I already mentioned this one. The standard deviation has the same units of measurement as the original data values. That can be really convenient when you're thinking about it. Right. Okay. There's an empirical rule that comes up, which I think is best summed up with this picture. If we have data, so if we have a bell-shaped distribution, wait, where's the, yeah. For data sets having a distribution that is approximately bell-shaped, that's the thing you're going to do a lot. You're going to look at data sets and ask yourself, is it bell-shaped? Is it symmetric? If so, we're going to call that normal with a capital N, and you're going to go, oh, that's great. That makes things easier for us. So assuming you have data that's approximately bell-shaped, then 60% of your data falls within 1 standard deviation, 95 falls within 2 standard deviations, 99.7 falls within 3 standard deviations. So what that means is, if we're looking at this graph, you've got your mean. Remember, X bar is your mean right here in the middle. And you go out 1 standard deviation either direction. So that's X bar minus S and X bar plus S. Remember, where S is our standard deviation. So we can see 68% of our data is falling within this middle portion where they're 1 standard deviation away. 2 standard deviations, 95% of our data falls within there, and 3 standard deviations, 99.7% falls in there. Now, these are estimates, but that can be really helpful for eyeballing things. If you're working on something and you know the mean and you know the standard deviation, you can go, oh, well, about 95% of my data falls within this point to this point, right? It falls within this range and can help you kind of sum stuff up. There's a more complicated version of that called Chebychev's theorem, but I think for this class it's a little beyond what we need to do. There are other ways of measuring deviations besides the standard deviation. So one of the things that happens in the standard deviation, remember I talked about those measurements where we measure the distance between the mean and the data point? Okay, that's a deviation. If you go through and you add up all those deviations, you get 0. It's just the way that it works mathematically, because that's how the mean is calculated. If you take all the data points and subtract the mean and then add up those, you get 0. So that's not very helpful. So what they do in the standard deviation is they take all those distances between the mean and the data point and they square it to make them all positive so they don't cancel each other out. So most of the time, that's the right way to do it in statistics. There are certain areas of statistics where they like to do it a little bit differently. So you can have, for instance, the mean absolute deviation, or MAD. Most people don't know that that exists unless you know about statistics, but it exists. But for this class, we're just going to stick with the standard deviation. That's what we need to know. But those of you going on and you're going to study other types of statistics because you're like, oh, I could make a decent career with statistics, you'll study those at a later date. Okay. Right. Okay. And I forgot last time, most of my classes get out at 10 till the hour. So last time I forgot, and I let this class out at 10 to the hour. But I made special note today that this class actually goes longer, so I don't want to cheat anybody out of their class time. So I'll try to make sure I stick around and give you that information. Okay. Okay, then we get a thing called z-scores. Z-score is super important, and I actually think z-scores are kind of cool. You can do some interesting things with z-scores that we don't really have any other way of doing, right? Like comparing things that seem completely different from each other. We can do that with z-scores, and kind of hard to do in any other way. So let's see, what is a z-score? A z-score, or standardized value, pretty much everyone calls them z-scores. A z-score is the number of standard deviations that a given value x is above or below the mean. The z-score is calculated by using one of the following. So this is the notation for the sample, and this is the notation for the population. In this case, the calculation is really the same. It's just, remember, we use x bar for the sample mean, we use mu for the population mean, we use s for the sample standard deviation, and sigma for the population standard deviation. So the actual calculation's the same, it's just the symbols are changing depending on whether we're talking about a sample or a population. That's different than the standard deviation, where the formula for a standard deviation of a sample is literally a different formula than the standard deviation for a population. That's why I pointed that out in StatCrunch, because you got to make sure you're using the right one. Here it's just a matter of using the right symbols. Okay. So what does this mean, right? It's a pretty simple thing to calculate. It's a pretty simple formula, but what does it mean? Every time you learn a formula, you should ask yourself, what does that mean? Because if you're just blindly using formulas like a magic box that I don't know what this is, it's some fancy formula, I'm plugging stuff in, you're probably going to end up using it wrong. So what is really going on here? Well, remember, x is a data value, x bar is your mean, and s is your standard deviation. So what are we doing? We're taking x minus x bar. That gives you the distance from your data value to the mean. We've talked about that a little bit now. That distance divided by the standard deviation tells you how many standard deviations your point is from the mean. So it's what I was talking about a minute ago. The z-score is literally your measure where you put down your 12-inch ruler that you use to measure the wall, and you pick up your standard deviation, and you start at the mean, and you just put your standard deviation down to make measurements until you get to the mean, and you say, oh, my data point is 2.7 standard deviations away from the mean. Then you know like how far from the middle that standard deviation, that data point is. Now, this is a little bit different than what we've done so far, and I see students get confused about this. The mean is a calculation that includes the whole set, right? The median doesn't use the whole set directly, but it's a reflection of the whole set, right? The standard deviation uses the whole set. The z-score is a score particular to a data point. In other words, for the mean, the median, and the standard deviation, those apply to every single point in your set. But every single point in your set will have its own z-score. Does that make sense? Like some of them will end up being the same, but by and large, you're going to get a bunch of different z-scores for the different values in your set. So it's a different way of thinking about data. The z-score tells you about an individual data point, whereas the mean, median, and standard deviation tell you about the set as a whole. So I see students that they get confused by doing one and then doing the other, and they don't recognize that the z-score is for an individual point. It's not for the whole set. Okay. So how would you calculate a z-score? Well, let's do some. So let's go back and let's make an example. So let's say we've got, let's see, an English class and a math class. Okay, so you have two buddies. They're both taking classes at college, and they both just got the highest grade on their exam. And they're bragging to each other, and they're trying to, each one's trying to outdo the other one, going, well, yeah, but yours is cool. That's great. You got the highest grade, but it's hard. My class is harder, so me getting the highest grade is even better. And then they're just going back and arguing about this. Okay? Well, this happens a lot in life where you'll hear arguments, and then, like, if you know some statistics or some math, you overhear this, and you're like, they're having a dumb argument. If they just used a little bit of math, they could just settle this once and for all, right? Sometimes they make this sort of messy on purpose. Like, for instance, sports and news. These are all 24-hour cycles now. Like, sports channels are going 24 hours a day. News channels, 24 hours a day. So sometimes they just need words coming out of their mouths. They just need to speak. So they intentionally, like, don't get to the point because they got airtime to fill. Okay? Like, for instance, on sports, you ever listen where they're like, okay, who's the best basketball player of all time? And then you got some people, well, I think Michael Jordan's the best basketball player of all time. Well, I think Kobe Bryant's the best basketball player of all time. Well, I think LeBron James is the best basketball player of all time. Well, I think Wilt Chamberlain's the best basketball player of all time. And these people sit there and argue over it, but it's a silly argument because what does that even mean? What does it mean to be the best basketball player of all time? That's what a mathematician or a statistician or a scientist would come up and say, what are you talking about? You're using words that don't mean anything, like best. What you think is the best may not be what he thinks is the best, may not be what she thinks is the best. A mathematician would say, well, what do you mean by best? Is the best player the one who won the most championships? It is the one who scored the most points throughout their career? Is it the one who averaged the most points per game? Is it the one who's kind of well-rounded and had the most triple-doubles? Is it the one who got the most free throws or the three-point shooting? Like, there's lots of different ways to measure. The word best is really just a way to have an argument. It's not really a way to come up with anything substantial or meaningful. It's just something to talk about and have sounds coming out of your mouth while you're being recorded as a ESPN commentator, right? If you really wanted to get to that bottom of the argument, you'd say, well, we're talking about people who scored the most points per game because those people were consistent and the most helpful to the team or whatever, right? You make some kind of a case. So anyways, you want to pin down when you ask questions and you try to study something, you want to pin down the meaning of what you're asking, right? And I see students do that where they don't really ask good enough questions. They'll ask something along the lines of the best basketball player rather than asking, well, who scored the most points per game or something like that. Okay, so let's say in the English class, this person scored a 91, and then there were other people in the class scoring like this. Okay, so in the English class, those are the scores. And here's some of the math scores. Okay, so we've got the English person and the math person. They meet up at break, right? They're going to maybe go grab lunch, get some pizza. And they're both bragging, man, I got my test back and I got the highest grade in the class. And English person says, oh, well, that's good, but I got a 91 on my test. You only got an 89 on your test. And then math person says, yeah, but they were different tests. You can't just compare it that way. My score's lower, but I think I did better compared to the rest of my, like I was further ahead of the students in my class than you were in yours, right? And they're just kind of going back like people do sometimes, like giving each other the business, trying to figure out who actually did a better job here. Well, what we could do is calculate the z-score. Now, this is weird. Like, what other way would you have to compare things? You wouldn't, because usually the units would mess things up. The units in this class would be different. You might say, well, aren't they just the test points? Right, but these are for a different test than these ones over here. They're not really meaningfully translated back and forth. That's one of the powers of the z-score, is the z-score has no units. The units cancel out in the calculation, and you're left with a ratio. You're left with a measurement of how many standard deviations did you outperform the middle. Okay, so let's do this. Let's calculate our summary stats for columns English and math, and we'll compute those. Okay, so what we have here is, show you how to do this. Let's go z-score. Those problems are from my algebra class I taught at 10. Here we go. So for a z-score, we've got, let's summarize our information. So we've got English, and then we've got our math score. So I'm going to compare these. I'm going to show you how this works. Okay, so for the English class, we're talking about the score. That was, what, a 91? Let's bring this over here so I can follow. That score was a 91. The other one was an 89. Okay, so we're picking the score that we care about. We're trying to compare these two high scores because these two guys are trying to figure out who did better. So we take the 91 and the 89. Those are the scores that we're computing a z-score for, because remember, each data point in your data set has a different z-score. So we care about those high ones. Okay, so the English has a score of 91. The math has a score of 89. The mean for the two are what? So we've got a mean of 84.8 and 73.9. Okay, 84.8 and 73.9. So 84.8 and 73.9. Did I get those right? 84.8, 73.9. See how I'm just grabbing them from the mean here in my summary stats? It's giving me that information right here. Okay. So now I need to know, so we've got there were three things in our formula: the data point, the mean, and the standard deviation. Okay, so now I need to go over to the standard deviation. So, oops, we don't need that. Oops, we don't need that either. Where am I? Here we go. The standard deviation, which will be a lowercase s in both of these cases. So what was it? It was 4.8 and 6.8. Okay, so 4.8 and 6.8. Let's make sure I got those right. Oops, don't need those. 4.8 and 6.8. Okay, and I'm just being kind of, yeah, I guess that would be the right rounding there. So, okay, so now we want to do the calculation and figure out who has a better z-score, because in this kind of argument, that's what I would go with, is whoever had the better z-score. I would say, yes, you outperformed the other person. Where am I? Okay, so right here, let's do the calculation for the English score. So English would be that z equals, okay, so it's the data value that we care about, so 91 minus the mean, 84.8, over 4.8, which is the z-score, which is the, standard deviation. And if I get out my calculator, then 91 minus 84.8, 6.2 divided by 4.8 equals 1, rounds to 1.3 basically. So this is approximately 1.3. So the friend who did well in the English class scored approximately 1.3 standard deviations above the mean. Okay, now let's figure it out for the math individual. So the math individual has z equals, okay, now this case, the score that we care about is 89 minus the mean, which is 73.9, over a standard deviation of 6.8. So let's see, 89 minus 73.9 divided by 6.8 equals 2.22, or 2.2 we'll go with. So this is approximately, I'm saying approximately because I'm rounding my answer, approximately 2.2. And this settles it, right? It's pretty hard to argue with this. The math score, even though the math person didn't even get in the 90s, they still outperformed the other students in the class by more than the English student did, right? So, you know, this is what I mean when I say you can settle these silly kind of arguments if you just pick your measurement and apply the appropriate one. In this case, I would say I'm hard-pressed to find a better way to compare these than a z-score. Yes, the 89 score was lower than the 91, but they're in completely different classes, so that it's not really fair to compare those because it may have been a lot easier to get the 91 score than to get the 89 for the math. And that's backed up by the fact that the person in the math class scored 2.2 standard deviations above the mean, whereas the English person only scored 1.3 standard deviations above the mean. Okay, that's pretty helpful. That's a pretty great use of a z-score, which is simple to calculate, right? There wasn't a lot of complicated math in here. It's not like doing the quadratic formula. It's a subtraction and a division. Pretty straightforward. And then you can compare things that otherwise you'd have a pretty hard time comparing, right? It would be difficult to compare otherwise. So that's why we're saying once a data value, we can use the z-score as a ruler, as a measuring tool to measure how far away a particular value is from the mean. And it just, by and large, is kind of a rule of thumb. This is not like a hard set rule. Really, most things in statistics are just rules of thumb. Once you get more than 2 standard deviations away from the mean, that's when you start paying attention and going, oh, this is kind of an extreme value. Maybe I should keep my eye on this. Maybe I should look closer at this. So that's what, outside the 2, you get unusual values, whereas in here they're a little more ordinary. Okay. Okay, percentiles. I cannot talk about percentiles in 7 minutes. That's not, well, I may have to because we're not going to be able to get through everything anyway. So that's right, because this class only meets a handful of times. Percentiles give you, basically, you want to find what percent of the data is above or below this mark. So SAT scores are given this way, or they used to be. I don't know how SAT scores are given these days. But they used to be given as percentiles. So I remember when I got my SAT scores, you get your scores, and it says you scored in the whatever it is. I'm making this up because I don't remember my SAT scores from long ago. But they might say you scored in the 90th percentile, right? So that means that 90% of the data is below my score, meaning I scored in the top 10%. Right, or whatever the value is that you're looking at. So percentiles are a measure of location, denoted P1, P2, up to P99. That number is representing the percentage, which divides sets of data into 100 groups with about 1% of values in each group. Right? So the 75th percentile means 75% of the data is below that value. 90th percentile, 90% of the data is below that value. So that's where you get a number from the SAT score, but you can also go, oh, I finished in the top 10% of people who take this test, or I finished in the top 5% or 3% or whatever it is that you end up doing. That percentile is helpful because otherwise if they say out of 600 possible on this part of the test, you scored 370 and you're like, well, is that good? Is that bad? I don't know. What is that supposed to mean? But if you know, well, I scored better than 90% of the people who took the test, you go, okay, that's not bad. It's not great, but not bad, right? What about the 50th percentile? The 50th percentile, we already know a name for that. It's the median, right? The median splits the data in half. The 50th percentile has 50% of the data below and 50% of the data above. The 50th percentile is also your median. So now we're seeing we create two different things, and every once in a while they match up. Look, that median's the same as the 50th percentile. So some of these ideas are very related to each other. It's just that the percentile is a very specific way. Like we can measure something and say 33% of the data falls below this point right here, right? And that's a good example of why that's useful. Comparing SAT scores. If you were just given your raw score, you wouldn't really know if that's good or bad. But once they tell you you're in the top 3%, you go, oh, okay, I'm going to go show my parents this SAT score, right? Because that's impressive or whatever. So that's what percentiles are all about. You'll mess with those along the way. What do we have? A few more minutes. So you can do one of two things. You can, when we're talking about percentiles, you can say, I want to know what the 90th percentile is. So in other words, I want to know the point where 90% of the data is below that. Or you can take a data point and say, what percentile is this? One of those calculations is easy. One of the calculations takes a little more work. So just kind of pay attention to which direction you're finding because one's trickier than the other, right? But just be careful and you'll be fine. Quartiles? Quartiles are just percentiles that happen in quarters. So what does that mean? Well, a quarter is a fourth. So 25th percentile, 50th percentile, 75th percentile, 100th percentile. Although the 100th percentile is just always your top value, right, in the data. So that's not really that spectacular. But that's all the quartile is you're coming up with percentiles where the percentile is 25, 50, 75, and 100. It's all that really means. A couple more minutes. We've got the 5-number summary, and then we can use that to create a box plot. They used to be called box and whisker diagrams. They just call them box plots now. But that 5-number summary includes the minimum value, first quartile, median, third quartile, and your maximum value. When you do these summaries in StatCrunch, it gives you all those plus some more information. So in StatCrunch, when you calculate this, it's giving you the 5-number summary plus a little bit more, really like the what? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11-number summary is what we're getting here. And what the box plot is a way of visualizing the values for your 5-number summary. Right? Because if we look at one, this representation of how you create this box, this is your minimum value, this is your maximum value, and then you create a box in the middle that stretches from your quartile 1 to quartile 3 with your median in the middle. This gives you a pretty good way of understanding how your data is spread out. Because notice how this side is longer than this side? Well, this right here is 25% of the data. Here's 25% of the data. Here's 25, and here's 25. This distance here is a whole lot shorter than this distance, which means the 25% of the data at the bottom is very compressed, whereas the 25% of the data at the top is very spread out. It's kind of like what we would see with ages in this class. We would see the ages at the bottom. Well, let's just assume there's no 14, 15, 16, 17-year-olds. Let's just say it starts at typical class where everyone's at least 18. You're going to see a lot of compression down here because a lot of people are 18, 19, 20. So this would be very short. And on this side, it'd be very long because you'd be getting into those people in their late 20s, a couple people in their 30s, maybe one person in their 40s, someone in their 60s. Would be very spread out on this side. And then in here, the box, that's the middle 50% of your data. And you can even see that cut up. That means this low side, this is still a little more compressed than this part right here. So you could see if we were to graph this, you would see that skewed behavior where it's steep on this side and then sort of stretching out with a long tail on this side. Okay. Let's see. And then we get into outliers. So let's just leave. Is there much to say there? Actually, no. I think that pretty much wraps up that part of, yep, that wraps it up. So we'll stop there. Yeah, make sure you're doing your presentations. Make sure you're coming to ask me questions. Make sure you're watching these videos, right? I know some people don't watch them live, although I highly recommend you come to class so that you can ask questions and stuff like that. Some people watch them later. Make sure you're getting stuff done. This is a fast-moving class and don't want people to get left behind. So, good work. I will see you Tuesday. Okay.